Hello everyone, welcome to Pratibha Tech. In this video, we will solve the problem of the day question on Geeks for Geeks for 5th May 2023. The problem statement for today is good subtrees. Let's now open this problem to solve it. Let's go through and understand the given problem statement. It says, you are given a root node of a binary tree and each node of the binary tree is assigned a value. You are also given an integer k and you have to return the count of good subtrees of the binary tree. Good subtree is a subtree that such that the number of distinct values in this subtree is less than or equal to k. In note, it is given that subtree of a node consists of the node and all the nodes of the subtrees left and the right child of that node if they exist. Okay, so the problem statement is asking us to find the number of good subtrees in a binary tree. A good subtree is defined as a subtree in which the number of distinct values is less than or equal to the given input as k. Okay, so let's go through and understand the given examples. So the first example says this is the binary tree. Here k is 2. That means all the subtrees where the value of all the nodes, and that means each subtree, if the value is less than or equal to 2, that will be the number of distinct element, if that is less than or equal to 2, then that subtree will be considered as a good subtree. So here it is saying that output is 4. How we are getting output as 4? We can see all leaves, that means 3, 4 and 5 form good subtree as the number of distinct values in subtree is 1. So if we take all the leaf nodes as a subtree, then we can see here only one element is there, so there is no point of having more than one distinct element. So here the distinct element count is 1 in all the leaf node. So these 3 are the part of good subtrees. So count is 3 here. After that, now the subtree which starts at 2, this one, and has 3 as the left node. So now we are considering this subtree. This starting from 2 and 3, this one. This one is also a good subtree because the count of distinct element is 2 here, and the maximum limit given in the input, given in the problem statement, is also 2. So even this we can consider this subtree. That means 2 and 3. Here distinct element count is 2. So this is the fourth one. If we try to consider this one, then this subtree which is starting at 2 and having child nodes as 4 and 5. So here we see the number of distinct element is 3. That means 2, 4 and 5 all are the distinct element. So this we cannot take because k is given as 2. Okay, so even if we consider the top one, so here we get more number of distinct element which is much higher than k, which is 2 here in this example. So we have got total 4 count, 3 leaf node and 1 subtree starting with 2 and having 3 as the left child. So total count is 4. That's why the output is 4. If you look at the second example, so second example says this is the given binary tree. So here and here k is 1. That means the number of distinct element in a subtree that is allowed is 1 only. So here also the output is 1. Here also the output is 4. We can see that leaves 2 and 2 form a good subtree as the number of distinct element in the subtree is 1. So when we are looking at this 2 and this 2, so if you consider this as a subtree, then here the number of distinct element count is 1. So that's why these two are considered as a good subtree, which is equal to k, which is given as 1. Now both subtree which starts at 2 and has 2 as the child node. So now this subtree and this subtree which is starting as 2 and having a child node as 2 on the right side as well. So this is also these also can be a part of good subtrees, because if you see the number of distinct element in this subtree which is also 1 only, because 2 and 2 we have elements here as 2 and 2. So how many distinct elements are there? Only 1, which is 2. So even these two are considered as the part of good subtrees. So here also we have got the number count as 4. 2 leaf nodes and 2 subtrees which is starting at 2. Okay, when we take the subtree which is starting at 1, then here we see the number of distinct element is 2, but here the value of the k is maximum we can take is 1. That's why we have not considered that one. Okay, so I hope this problem statement and this given example is clear to you. So for solving this problem, the logic which we will use is based on the fact that subtree is a subset of the binary tree rooted at a given node, and the number of distinct values in a subtree is the number of distinct values in the union of the sets of distinct values of its left and right subtrees, as well as the value of the root node itself. Okay, so therefore we can traverse the binary tree using DFS at each node and recursively traverse its left and right subtrees to get the sets of distinct values in each subtree. We can then create a new set and all the values from the left and right sets as well as the current node value we will add to it. If the size of the new set is equal to or less than k, then we increment the count of good subtrees. By the end of this traversal, this count variable will contain the number of good subtrees that is there in the given binary tree. Okay, so this approach we will be using for solving this problem. So whatever I have just explained the approach, with that I have prepared one solution. Let me just copy the solution here. It is exactly the same whatever I have told the approach. So here also I have added comments so that it becomes easy in understanding. So what we are doing here, just a minute, let me replace entire thing. Yeah, because that method signature was repeating twice, that copy paste was not done properly. Yeah, so what we are doing here, if you look at this solution, this uses a depth first search approach to traverse the binary tree recursively. The good subtree, this method takes the root node of the binary tree and the integer k as the input. It initializes a global variable count to 0, which is used to keep track of the number of good subtrees. It then calls DFS method, which recursively traverses the tree and finds the number of good subtrees. Finally, it returns the number of the count of the good subtrees which is there in the binary tree. So whatever is that global variable count which we have initialized, so this will be updated in this DFS method, and whatever is the updated value will be there, so that will be returned as the count of good subtrees. Okay, if you look at this DFS method takes a node and an integer k as input and returns the set of integers. Okay, the set represents the distinct values in the subtree rooted at that node. If the node is null, an empty set is returned. Here when we are checking if the root is null, then we are creating a new set. So we are saying that it is returning an empty set. Otherwise, the method recursively calls itself on the left and the right child node to get their sets of distinct values. It then creates a new set with the name current set and adds all the values from the left and the right sets as well as the current value node. So whatever the current set we are creating, we are adding to this set all the values which we have got from left set and the right set, that means left subtree and right subtree, and to that we are adding even the current node value. If the size of the current set is less than or equal to k, then the subtree rooted at the current node is a good subtree and the count variable is incremented. Finally, the method returns the current set. When this condition is satisfied, the count is incremented, which is indicating that we have got another increment in the value of the count of the good subtrees. So finally, the current set, that variable is returned from this method. So mostly this will be called recursively, and since this method is even getting called here and we are updating the count variable, so once this loop terminates, once this method all these recursive calls gets completed and it comes out of this loop, then whatever is the updated value of count, that we will return from this method. Okay, so this was the coding part of it. That's it. That's it in the coding part. Let me try compiling this code. So here we can see we have got correct output for this given input. Let me try submitting this solution. So here we can see all the test cases are passed. So this was the solution in Java. So when we talk about the time complexity of this solution, it is in the order of big O of n log n in the worst case, where n is the number of nodes in the binary tree. This is because the code performs DFS traversal of the entire binary tree, visiting each node once and creates a new set of at each node. In the worst case, the DFS traversal will visit every node in the binary tree, leading to the complexity of big O of n. Additionally, at each node we are adding the elements of the two sets and then adding one more element, that is the node value, to create a new set. Since the number of elements in the set can be up to n, that is the number of nodes in the binary tree, it takes big O of n time. Therefore, the time complexity of the code is big O of n log n. Since the depth of the recursion can be up to n log can be up to log n, because it is a tree. Okay. So this was a Java solution. Even I prepared C++ solution. So let me move to C++ editor. Let me just copy the code here. Here also the logic is completely same. Only the difference between C++ and Java related to some syntaxes, that is here. There we used class, here we are using pointers, all those things. But here the logic is completely same. We are initializing the count variable. We are calling this DFS method. Inside this DFS method, if it is null, then we are returning empty set. Then we are calling this method recursively for getting the left set and right set. And once this is done, then we are creating a current set. To this we insert all the values of left set and right set and the current node value, and check if for this current node, that means current subtree, if the current size is less than or equal to k, then for that particular subtree we count it as a good subtree and we increment the count variable by 1. And when this complete loop terminates all these things, then we return the count set, we return the current set for this recursive calls. And inside this one, the count variables keep on updating. So whatever is the updated count, when we come out of this method, so that will be returned here as the count of good subtrees. So the logic is completely same. Let me try compiling this code. So here also we can see we have got correct output with this C++ code. Let me try submitting this solution. So even with this C++ solution, it has covered all the test cases. So this problem has been solved successfully in both C++ and Java. So I'll provide the link for this question and the link for the solution code in Java and C++ in the description box. Please do check that. That's all in this video. Please like, comment and share the video, and please subscribe to the channel for more upcoming videos. Thank you for watching.